Good morning. This is K. Prashant Kumar, working as Assistant Professor in Department of Computer Science and Engineering, Honors. Today, we will learn about the topic called backtracking, in which backtracking we are going to see the 8-queen problem and sum of subset problem. So it comes under CO3 part in design and analysis of algorithm. So before learning 8-queen problem, we need to learn about 4-queen problem, how it works. So see here, the 4-queen problem consists in placing the 4 queens on a 4x4 chessboard. So we have to place. So see here, there is four rows are there here and 4 columns are there. 4 rows and 4 columns. So this is a 4x4 chessboard, where we have to place the 4 queens in a 4 rows and 4 columns. Okay, 4 rows, 4 columns, and within a 4 diagonals. So this is a 4x4 chessboard that we need to place a 4 queens, such that, see here, no 2 queens can attack each other. That is, no 2 queens are allowed to be placed on the same row, same column and same diagonal. So this is the constraint here. So 4 queen has to be placed such that no 2 queens should attack each other. That means that after placing a q1 here, we should not place the other queen in the same row, in the same column and the same diagonal. So this is the constraint here. So how we are going to construct here? So see here. So this is a 4-queen problem. Here we need to construct like this. Is it possible to construct? Yes, it is possible to construct. How? Let's try here. So see here. So in the first 4x4 chessboard, so here it is there q1. So q1 we are placing in the first row here. After placing the q1, we should not place any queen in the same row, same column and same diagonal. So we should not place here. And what are the available space for placing the q2? So there is a 2 available spaces are there, 1 and 2. Within these 2 available places that we can safely allocate q2 here. Next, see here. So q2 we have allocated in the second row, first place. After placing this one, there is no place for q3 in the third row. So see here, in the third row there is no place for the q3 to be placed. Then what we have to do? At that time we have to backtrack here. Backtrack and change the position of q2 to next place. Okay, since it is a available space. So see here, in the third row q3 cannot be placed because there is no safe place. So we need to backtrack the q2. So we are changing the position of q2. So see here in the next slide. So we have changed the position of q2. After changing the position of q2, there is a available space for the q3. So we can place a q3 at the safe place. After placing the q3, there is no space for the q4 to be placed in the fourth row. Again what we have to do? We have to do the backtracking. But see here, to backtrack this one to the leftmost position, so q1 can attack, so we cannot backtrack here. Next, to move a q3 to the rightmost position, then diagonally this q2 can attack. If I move here q3, again same column will be there. So q2 can attack with the same column. So there is no possible position for the q3. And for q2 also, for backtracking, it is in the last position. We cannot backtrack here. Okay, if I do here, then same row q1 can attack. If I do here, then same row q3 can attack. If I take this one q2 here, again see here, diagonally q1 can attack. So there is no possible spaces for the q2. So there is no possible spaces for the q3 and q2 to change the place. Then we need to backtrack the q1 here. So see here, so we are changing the q1 position from here to here. From here to here we are changing here. Now, is there is a available space for the q2? Yes, there is an available space for the q2. So this is an available space. So this is an available space is there. Okay, so we can place here. So see here, q2 is placed here. Okay, next, is there is a available space for the q3 to be placed in the third row? Yes, we can place a q3 here. So see here, in the next we have placed a q3 here. Is there available space after placing the q3 for the q4? Yes, is there available space. So in the next we have placed the q4 here. So this is the construction of 4 by 4 queen. So what is the solution vector here? First queen is placed in the second column. So this is a 2. Second queen is placed in the fourth column, and third queen is placed in the first column, and fourth queen is placed in the third column. So solution vector is 2 4 1 3. 2 4 1 3. And this is not only the solution, but there can be many solutions can be obtained. Many solutions can be obtained. Next, what is the methodology we have used here? Systematically searching for the solution and building a solution one at a time, checking the each queens to be placed on a each row, each column diagonally, and we are cross checking each and every queens so that no conflicts will occur. If conflicts occur, what we will do? Undo the last step and try for the next option. So what is the constraints we have used here? So the methodology we have used is backtracking, and there is a constraint to we have used. The two constraints, the two most important constraints we have used in the backtracking is that, so explicit constraints and implicit constraints. So backtracking process is basically used to explore all the possible values of the current position and validate the feasibility of the solution by backtracking the necessary exploring options. So it is going to explore each and every option such that no conflicts will occur for the queens to be placed on a 4 by 4 chessboard. Okay, 4 by 4 chessboard. So this is the all the constraints it will follow, and until and unless we get the feasible solution, it will backtrack each and every positions of the queue. Okay, so this is the backtracking methodology. So two constraints we have used is, first constraint is the explicit constraints. Explicit consisting these constraints have the S of I is equals to 1 2 3 4, that means 4 columns. Within a 4 columns from 1 to 4 we have to place a queen here. Okay, we have to place a queen. Next, so see here, x1 x2 x3 x4 or xi consisting of 4 queens, in which each queen should be select from a one column of set I to be placed. So within this set 1 to 4 columns we have to place the queen in any one of the column. So this is the two constraints here. So this is the first constraint, that is explicit constraint. And what is the implicit constraint? Implicit constraint is that no two queens should be placed in the same column, same row and same diagonal. So these are the two constraints we have followed in the backtracking methodology to solve the 4 queen problem. Okay, and this is the backtracking technology. So if there is any conflicts here after placing a queens in a diagonally, if there is a conflict, we will apply the bounding function here. How we will apply here? So this is the state space tree. So this is the state space tree, where the state space tree is consisting of 4 queens with attacks. So these are the possible attacks. So see here, so first queen after placing a 4 most positions, the second queen can have the first queen can have 4 positions, the second queen can have only a 3, at most 3 positions can be placed. After placing a q2, q3 can have at most 2 positions to be placed. Next, q4 can have only the 1 position. So what are the possible? So this is the possible solutions where 4 queens can be placed with attacks. So attacks can be possible. So this is a diagram of state space tree. Next, this is the bounding function. So bounding function, what does it tells? After placing a q1 here, x is equals to 1, q1 here. Okay, if we place a q2 in the same diagonal, then there is an attack will happen. Okay, we should not place in the same diagonal. So we will use the bounding function. So backtracking technology, and again we will go and we will search for the alternate options. So this is the bounding function we have applied here in order to solve the conflicts conflicts between the queens. Next, what are the solution vectors we have obtained previously? 2, 4, 1, 3, and there can be a mirror image is also one of the solution vector for the 4 by 4 queen. Okay, 4 by 4 queen. So mirror image. So what is the mirror image? 2, 4, 1, 3. The mirror image is 3, 4, 1, 2. So this is also another solution for the 4 by 4 queen. And this is the iterative backtracking technology, this algorithm we have used. So what are the constraints we have used? Those constraints, based upon these constraints, okay, these constraints to check whether two queens should not be placed adjacently, that is within the same row, same column and same diagonal. So by following the constraints, we have designed a iterative backtracking algorithm which will be helping us to solve the problem of 4 by 4 queens problem. So we can so there is a comments here, comment section tells us each and every line what does it does. So you can trace back this one algorithm and you can analyze this algorithm. Next, recursive backtracking algorithm also which will help us to solve this 4 by 4 queen problem. By iteratively it will check, okay, each and every queen whether it has a conflict or not. If conflict occur, it will call the function called this backtrack. Okay, so this is the recursive backtracking algorithm. Next, so we will see the applications. So what are the applications? So producing the number of permutations. Next, so these are some example. So this is an example problems, n queen problem, sum of subset problem, all these are examples of this 4 queen, okay, 4 queen problems. Next, similarly we are going to construct a 8 queen problem. Can we construct? Yes, we can construct the 8 queen problem by following the constraints of 4 by 4 queen. By following the constraints of 4 by 4 queen, okay, same constraint, implicit and explicit constraints, we can construct 8 queen problem also by following the constraint, that is no 2 queens should be placed in a same row, same column and same diagonal. So by following this constraint, we can design a 8 queen problem on a 8 by 8 chessboard. So see here, so we have to check the safest position, and all queens has to be placed in the safest position by following the constraint. Okay, so all these things whatever we have discussed, the same methods we will apply in the 8 queen problem also. To solve this, we will use the backtracking technology. Same backtracking algorithm will be used, in which implicit and explicit constraints will be used to solve this problem. Next, what is the solution can be obtained? So see here, so this is the solution for the, so this is the one of the solution. It is not a unique solution, but it is a one of the solution for the 8 queen problem. So what is the solution vector here? You can see here. So this is the solution vector 3, 6, 2, 7, 1, 4, 5, 8. So this is the one of the solution. Okay, we can try for the another solutions by applying a different explicit and implicit constraint. We can have a different solutions can be obtained. So what is the time complexity for here? So see here, the time complexity is order of m plus n. So order of m rows and n columns, so it gives order of 2 to the power of n, whereas space complexity is all log n times it takes. So this is the 8 queen problem. Okay, this is the 8 queen problem. So same n queen problem can also be constructed by using a constraints, by following the implicit and explicit constraint, that is no 2 queens on the same row, same column and same diagonal. So to check, in order to check whether the 2 queens are diagonal or not, we will use this equation. We are going to use this equation. Okay, we are going to use this equation to check whether the 2 queens are diagonally or not. So that represents I comma j and j comma l. Ith row, okay, ith row, jth column. Next kth row and lth column. So by using this one, we are going to check the. So by using this equation, we are going to check whether the 2 queens are diagonal or not. Okay, so this is an algorithm to place whether the 2 queens, okay, two queens in a n by n chessboard. So this is a constraint we are using, whether the two check is two queens are in the same column or same diagonal. So trace out this algorithm, it will be okay. In the next comment section also it describes that each and every line of the code. Next, n queen algorithm also, okay. This algorithm is going to check whether to place a queen in a one column, okay, to place a queen in a one column. If so conflicts occur, we will check with the another options. So this each line of the code is explained with the help of these comments. Go through this and trace out this one and analyze this algorithm. Okay. Next, sum of subsets. So sum of subsets is the another topic where we have to check a selected from a given set of sum adds to the given number. So we have to find a subset of elements such that that subset of elements adds to the number k. Okay, so we will use the backtracking algorithm. Next, sorry. Next, so this approach is going to follow the, so comes with order of 2 to the power of n possibilities. Now next linear time it is going to take as order of n. So how we are going to find this one? So see here, this set is going to have a set of numbers are there. So the value will be given. So for this value, if we add a sum of numbers here, if we add a sum of number, these numbers has to equal this number, that is 35. Okay, so we have to design in such a way that the set of subset of given set, okay, subset of the given set should give a value, the sum of the value 35. Okay, we need to select numbers from a set. Next, so what is the bounding function we are following? So this is the bounding function we are following. So bounding function consisting of sigma wi xi, sigma k and sigma wi, where it represents sigma wi represents the weights, xi represents the values, k represents the index value, sigma wi represents the sum of given numbers. So this is the bounding function we will be applying for the sum of subset problem in order to solve this. After solving this one, so the bounding function will look like this. Okay, the bounding function will take a xi is equals to 1, x1 is equals to 0, x1 is equals to 1, x1 is equals to 0. It represents if the item is found, okay, we will increase this tree formation in the leftmost derivation, whereas if the item is not found, we will increase the tree in the rightmost derivation tree. So by solving this one, okay, by solving this subset tree, fixed tuple, okay, fixed site tuple, we are going to solve this sum of subset problem. So see here, so this is an example that we have taken. So see here, sum of weights they have given here 7, 11, 13 and 24. Okay, if we add these numbers, okay, sum of subsets, for example, if we add 11, 13, 7, it will be equals to 31. If we add 27 and 7, it will be equals to the 31. Next, no number, okay, other than these two, no other number is there. Okay, if we add it, the sum will be a 31. Only the two possibilities are there. How we are going to generate, how we are going to check this one? By using the bounding function. So first we will initialize wi xi to the 0, next k value to the 1, so this is the k value, so this is the wi xi, next this is the sum of wi xi. If x is equals to 1, if item is found, if x1 is equals to 0, that means item is not found. So we will apply this bounding function. Okay, first weight, so what is the weight 1? Weight 1 is equals to 7. So first one is equals to 7. Next, k plus 1. K plus 1 means already previously in the note 1 is there, so 1 plus 1 2. Next wi minus wk, that is 7 minus 55. So here 55 is there. 7 minus 55, that is 48. Next, we should not consider the weight here. So initially 0. Next, k plus 1 means 1 plus 1, 2. Next, 7 minus 55, 48. Next, x2 is equals to 1. That means W2. So what is the weight here? W2 is equals to 11. Similarly, we have to follow this one. And W3 is equals to 1. Weight 3 is equals to 13. Next, W4. So this is x4 is equals to 1 and x4 is equals to 0, right? So W4. So what is the W4? 24. X4 is equals to 1 means the weight 24 has to be considered. X4 is equals to 0 means we should not consider this one. If we follow like this, okay, if we follow the same methodology here from top to bottom, ultimately we are going to get a desired sum value, that is 31. If we get this one, so this is the one of the solution. Again, if we go on solving this one, see here, similarly we will get a 30. So 31 we have got here. So these are the two possibilities. So see here, 31 when we got here, when we place x1 is equals to 1, x2 is equals to 1, x3 is equals to 1. Next, here we got another solution 31. How we got here? So see here, by applying the x1 is equals to 1, x2 is equals to 0, x3 is equals to 0 and x4 is equals to 1. So x1, x2, x3 and x4. So we are adding the x1 and x4. So see here, x1 7 and 24. 7 and 7 plus 24, 31. Here x1, x2, x3 is equals to 1, right? That means 7 plus 11 plus 13 is equals to 31. So this is the sum of the value. In this way we need to apply the bounding function and we need to solve the sum of subset problem. And there is also another problem. You can apply the bounding function and you can solve this problem. Okay, example 2, and this is the algorithm. We have sum of subset, okay, algorithm, which is used to apply the bounding function and which is used to solve the sum of subset problem. So you can trace out this algorithm and analyze this one. Next, sample questions regarding this: what is the sum of subset problem and how we have to define, and what is the space tree, and this last thing you can take it as homework problem and you can solve this one, okay, by applying the bounding function. By applying the bounding function you can solve this one. Okay, so this is the topic about 8-queen problem and sum of subset problem. Thank you.